So, hello everyone, and welcome to the second meetup of the Hungarian C++ community. Today we'll have two presentations. First, Gábor is going to... He's Gábor. He's going to talk about the future of C++ compile time reflection. And then we'll have Attila, who's going to talk about, or rather show us an interesting way of defining infinite sequences in C++. So, oh, and please feel free to take pictures or videos even. Gábor.
Hello everyone, thank you for the introduction, Matthew. So let's start. So I will talk about compile time C++ reflection, but first I would like to say a few words generally about reflection. Then I will mention regarding to C++ how we can do reflection currently with C++. Then we will take a look about the current standard proposals regarding the C++ compile time reflection. And at the end, I would like to show you the direction of my researches. So reflection is about meta information of your program. It's basically whatever you can imagine, what can you query from your program structure, the state of your program. You could query how many classes you have, for example. You could query how many enumerations you have in an enumeration class, how many fields you have, what is the name of the fields, what is the types of those fields in your class. Also, it is important that you can, for example, in Java you can query annotations, and in some languages you can query attributes as well. The most common use case is usually serialization. This is the first thing. The first thing you pops in my mind when we are talking about serialization is about reflection is serialization. Also, testing is one field of the usage of reflection. For example, different mocking frameworks and testing frameworks uses reflection. Let's say, for instance, the JUnit Unitas framework uses reflection to query all those members which have the test as an annotation. Also, some object relation mappings uses reflection, like the Java Hibernate, and also there are a lot of use cases. I don't want to take so much time with this. It is important to notice that most of the languages are having runtime reflection implemented. The problem with runtime reflection is that you have to add extra information to every object you have in your program to be able to do runtime reflection. This is completely against the C++ philosophy we have today, which is you shouldn't pay extra efforts. You shouldn't pay some efficiency penalty for things you are not using. In C++, this is the thing you cannot allow. This is the exact reason why the C++ committee decided to have a compile time reflection first. Then maybe on top of compile time reflection, some higher level reflections libraries could be implemented which could do runtime reflection as well. Also, it is important to mention that if we are talking about reflection, then the most powerful thing you can imagine is, for example, in PHP you have something like eval. So this is a really cool thing. You can execute any kind of code which is a parameter to the eval function. And this can be done, of course, just with interpreted languages. Okay, so we are here at the C++ land. Some of you might know this picture, it's my favorite. So, what we have right now in C++, we have some sort of runtime reflection, but this is very, very low level. We have the type ID operator. This returns std type info, which gives you nothing more but the name of your type. This is, we could call it reflection, but this is not that. It's just some really, really low level query. Also, we have type traits. We can say that these type traits are static reflection things. But they are not more than just some low-level queries. They are just something like a thing which is returning a Boolean. So it's, you can just query whether my class is an enum, a scalar, a pod, something like that. This is not reflection. This is really, really low-level stuff. We want more things. I mean, compared to PHP and other languages, this is really low-level. Here, there's an example about serialization, how we can do serialization today with C++. Here I'm using the Boost serialization library. We have a GPS position with 3 members, and then there is the serialize function, which is a template function. And the problem here is that we have to enumerate all the members of the GPS position manually. And this is what we don't want to do if we take care about maintenance. This is error prone and repetitive. We don't want to do this, but we have to with each and every new structure we introduce in our C++ code. Also, regarding to object relational mappings, there is the ODB implementation, which is a GCC plugin. And this is doing source-to-source transformation. So when you have a source file and you have a source file, then you apply ODB to it, and the new source file will be generated. Then you can use any kind of compiler to move on to the next step. This is a bit better, but still you are doing translations and compilation twice. Mocking, this is my favorite, my personal favorite, because my daily work, I'm spending a lot of time with writing unit tests, and this really freaks me out that I have to repeat always the signatures. So if you take a look, we have the class of turtles. Oh, sorry. Some problems. I shouldn't be so eager to push the buttons. So if you take a look, we have these function signatures here, and we have to repeat all of them. What happens if the interface changes in the old class? Then we have to repeat those changes, and we have to exercise our editor. Even if you are using Vim, this is a hard thing, but I would say that I don't want to do that. I wanted the compiler to do that instead of me. So the thing is that today we can have some sort of static reflection in C++, but we always have to add the metadata manually. So we have to use our editor, and some frameworks might help us. For example, the Boost Fusion is a framework to be able to register metadata manually. In this example, we are doing that exactly. We have this foo struct, and we are adding the descriptive metadata with Boost Fusion at abstract here. So the key is that we don't want to do this manually. We need somehow to do this automatically by the compiler. So this is exactly what the SG7 study group, which is responsible for C++ compile time reflection. They want this, of course, and the goal of their existence is to solve these problems you can see here. For example, generating common functions like the equality function is a kind of goal to achieve, but nowadays I would say that there's a new proposal written by Björn Sørstrup. It's quite recent, and I think this would supersede the reflection proposals regarding to this direction, because it is something like today we can have default constructors generated by the compiler, and in this proposal Björn suggests the same but with the equality operators. I think it's more elegant than to do this with reflection. From my point of view, the most important is the enumeration of entities, the enumeration of class members, the enumeration of enum values. I think this is the most important case. Before we would go deeper in details, I would like to show this in C++ 14. These two things. The first thing is a variable template alias. No, sorry, that's the second. The first thing is just a template alias. The standard introduced these two guys. I mean, this is just an example for the is-enum type trait, but it has been introduced for all the other type traits. I need to show you this because other slides will refer to these template aliases. This is nothing more just a shortcut, so you don't have to always write type name, then your type trait, then your type as a template parameter, then colon type. If you are familiar with metaprogramming, I'm pretty sure you have done this several times. So I was really, how could I say, furious when I had to type name always. So this is why exactly the standard community decided to come up with this kind of shortcuts to make the metaprogramming more easier. So this is the first proposal I would like to talk about. Andrew Thomas and Christian Kaiser are the authors. Basically, they want something like this. In this example, you can query the number of the members of your type. Here we have struct A, and we can see that this struct A has exactly one member. Also, there's another directive where I would say this is a type trait, which would give you back the name of the first variable you have in your class. I have to say that you must recognize this underscore v. Previously, you've seen that this is a shortcut to colon value. This is a variable template alias. This proposal is a kind of low-level reflection proposal. I would say it is low-level because you always have to provide an index for the directives. What I mean, you have to say that, okay, I want to know the name of the first, the second, the third, or the nth variable in your class. You can query, for example, the nth base class, the name of the nth base class of your class, the type of the nth base class of your class. You can query or you can get a member pointer to the nth member of your class. So let me come up with an example how this is imaginated, how you can imagine how this would work. Okay. So here we have a class struct A which has 3 members. The goal here is to summarize the members. We simply just want to add them, and as you can see, the summary of the addition will be 6. It's a really silly, simple example, but it is here to demonstrate that if you change the addition operation to some other operations, like for example a serialization operation, then you are more or less ready with the serialization problem, with the generic serialization problem. Up here, I'm doing recursive template stuff. So, this is the end of the recursion. I have a member pointer. This underscore v might be familiar to you. This means that we have a member pointer to the first member of our class, capital A, and it has a type which is not important for us, but what we can do with this concrete pointer is that we can bind it to an object. After we bound it to an object, we can reference the value. So this line here, what it does, it will reach the first member of our instance. Then during the center of the recursion, we are doing exactly the same, but we are not getting the first member, but the nth member, I would say. Then we are doing the recursion down again. And somehow we have to start the recursion. We will start it with the number of the members. I would let you to take a more look on this because it might be frustrating if I would just go away now. So, let me go on. The main problem, the main criticism of this proposal was that this is too low level. You have to do template recursion. You have to do so low level things. Some people just wanted to expose the AST into the language, and they wanted something like static for, static if, those really high level stuff. But the thing is that the standard community is more conservative than that. They want to step forward in really small steps. They want to reuse the existing template metaprogramming techniques. And what is happening here is exactly that. We are reusing the existing techniques. In this example, I just want to show you that it's not always needed to use recursive templates. In this example, I just want to summarize 3 numbers, but all during the compilation. So, there is a template struct, a template class. The first question, why is it not a function? It's not a function because you cannot partially specialize template functions. So this is the correct way to overcome this problem. You would have a wrapper class with a static member function. So what I'm doing here is that I'm ending the recursion here, and I'm just returning 0. But during the recursion, what I do is adding the summary of the tail to the head. This might be familiar for anyone who is familiar with functional programming and with this kind of list magics. Okay. Below here, I want to show you that it's possible to do the same without this recursion. Here, I'm passing an integer sequence, which is an integer sequence to a validate template. So this means that this integer sequence would be expanded to to just numbers from 0 to 3. So these templates will have 4 parameters: 0, 1, 2, and 3. And then what we do with these parameters is just creating the initializer list from these parameters. Initializer list have a constant expression constructor, so we can do this, the whole thing we can do this in compile time. After we have our initializer list constructed, then we can summarize the elements and add this to the accumulated variable called s. I'm showing you this because I want to demonstrate that you can do higher level reflection with this kind of techniques, even though you have just some low level reflection type traits. The reason why I show you this exact proposal is that this is the only one which has a reference implementation, and I was really lucky and happy to be able to observe this implementation. You might be wondering how these STD member list size and those kind of things are implemented. The idea is that they will be implemented with compiler intrinsics. This means that the compiler introduces hidden new keywords, and each and every keyword would be parsed, and then a new expression will be created. By general, when you add a new expression to your compiler, you have to take care about the parsing methods. In this case, you have to take care about each and every new hidden keyword you introduced. You have to take care about the semantic analysis, which means that you have to tell the compiler that you need a new abstract syntax tree element. You have to tell the compiler how to transform this new node, which is related to your new expression, to intermediate representation of the code. Also, you have to take care about the template instantiation rules, and these things are really high level. I cannot really jump into more details, but I just like to give you some high level imagination how this can be implemented. Some more details. For example, if you take a look at the guts of this whole AST and semantic analysis implementation, this is exactly got from the reference implementation. When we are at the point of building an expression of our reflection for our reflection case, by the time we already passed, when we already processed the reference type. For example, you remember these examples, we had the struct with capital A. So we should have a complete definition of our type by the time when we are trying to, So by the time when we are trying to use our reflection type traits, we have to have a complete type about our type. This is what's happening here. This C++ record decal might be. This might be familiar for some of you who have been dealing with the Clang AST API. This is a Clang internal, and this C++ record decal would give you all the information you need at this point, because you can have the ranges of the methods of your query type, and you just can get the distance. This is the number of the methods of this class. This is basically an integer literal, so you would create an integer literal expression, and you would add this to the parent type trait, reflection type trait expression here. So this is roughly how these reflection primitives type traits can be implemented. There's another proposal which is doing something similar, but you won't get the information by indexes, but you would get it in one big list. For example, a type name t ... would give you the list of the members, the name of the members, and type def t ... would give you the list of the member pointers and the list of the member types of those member variables. Personally, I think it doesn't really matter which one will be approved or which one is the concrete direction, because if you think more about this is basically the same to the previous one. You are just having this. Generally about reflection, it is said that a program is doing introspection when it is capable of observing its own state and its own structures inside. And this program is doing intercession when it's capable not just observing but modifying its own structure and state. Regarding to these proposals, what you have seen, we might say that they can do, in a way, intercession, because you can define new functions based on the reflected information. For example, you can define a serialization function for any of your types, but the thing is that none of the proposals are speaking about what to do with the reflected names. What you can do now with reflected names is nothing more than printing them out or something like that. My favorite problem is what I mentioned you, is that how to solve. I mean, my favorite problem is the mocking problem, where I would like to have a mocking framework which is general enough to have the repetitive work doing instead of you. So I really think that for that, you need to be able to declare variables and functions based on reflected names. And basically this is the direction of my researches. So I would like to have something like this. If you have a struct A, you might have struct B with exactly the same member variable named m_a, but probably if you are striving to a mocking framework, you would want to have a different type for that variable. This is just the tip of the iceberg. I would like to show you my imagination about the same you could do with functions. Here, I'm again using and starting to using these recursive templates. The start of the recursion is not fit on the slide, sorry about that. But this is the exact idea. Being able to reuse the reflected names like this, so you could be able to declare variables and functions based on reflected names. You would be able to create, for example, this kind of generic mocking framework, or even some other things like this. Here, we want to have a class D, which is the same as class C, but without its copy constructor. this is really futuristic stuff. I cannot tell you that what's the concrete usage of it, but maybe in the future we can tell. So I really think that such higher level reflection could be implemented with those lower level variable declaration based on reflected names. I'm really eager to hear your opinion and your ideas about this, and I would like to ask you to share your opinion and come to have a chat with me about this and about everything. I'm really open to hear your ideas and about everything, about Prezi, about this competent reflection things, and about declaring variables based on reflected names and functions. So, thank you very much for your attention. Probably you might have a lot of questions, I don't know. So, it's the time for the questions.